Welcome to today's class on electronic devices, energy bands and classification of matter. I am K.S. Chandra, PGT Physics, Jan Bishanapati. First, let us try to know what are the topics to be discussed. A brief introduction about the development of semiconductor devices. Next, we will go to energy bands in solids, energy band diagram, conductors, semiconductors and insulators, then intrinsic semiconductor, doping of the semiconductor, extrinsic semiconductor, N-type and P-type semiconductor, distinction between intrinsic and extrinsic semiconductor. So let's try to know the brief history of the semiconductor. First, let us try to know what are electronic devices or semiconductor devices. Semiconductor devices are electronic devices which are used to control the flow of electrons when current passes through them. Before 1948, this control of flow of electrons through the material was achieved by using electronic devices called vacuum tubes or vacuum valves. There are different vacuum tubes: diode, triode, tetrode, and pentode valves, depending upon the number of electrodes they have. Diode has 2 electrodes, triode 3, tetrode 4, and pentode has 5 electrodes. The flow of electron is from the heated cathode to anode only, and its flow is controlled or achieved by varying the voltage between its different electrodes using low tension battery, and they are placed in vacuum. So they are called valves, or rather vacuum valves. These vacuum valve tubes are bulky, that means large in size, operates at high voltage, even more than 100 volt, consume more power, having limited life and low reliability. In the latter part of the 20th century, semiconductor junctions like junction diode or PN junction diode, transistor, semiconductor transistors replace the vacuum valves as they are small in size, operates at low voltage, consume small power, having longer life and almost high reliability. These semiconductor junctions led to the discovery of ICs, what we call as integrated circuits. Even a large number of network of circuits can be combined and packed into a small piece, what we call as chips. We call it these as integrated circuits or ICs, which have been used in almost all the modern electronic gadgets. So semiconductor is very important and need to be learned. Now next, let's try to know about the energy band in solids. According to Bohr's theory, atomic spectra and the concept of electronic configuration, the electrons in an isolated atoms have certain definite discrete amount of energy corresponding to different cells and subcells. It means there are well-defined energy levels of electrons in an isolated atom. If large number of atoms are brought close to one another to form a crystal, they begin to influence each other. There is no appreciable modification in the energy level of the electrons in the inner cells, but there is a considerable modification in the case of energy levels of the electrons in the outer cell. This is because of the fact that valence electrons are shared by more than one atom in the crystal. Let's take up either silicon or germanium. Silicon being the most abundantly found in nature, let's take it up as silicon atom, which has atomic number 14, and its electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3ps. Actually, p subcell can accommodate 6 electrons, but out of that 6, only 2 are filled, 4 are empty. In order to know the splitting of the energy levels of the silicon atom or the silicon crystal, let's try to take the help of the graph of energy versus interatomic spacing, and in it let's take it that there are n atoms in a silicon crystal. Let's see the diagram or the graph. If the interatomic spacing of the silicon atom is very large, R, that means this R greater than D, that means somewhere here. Now we need to bring those atoms toward one atom in the crystal, which is situated at O. When we try to bring that atom from far away distance, not only in this direction but in all the directions toward the crystal, in all the directions. So let's try to bring closer and closer toward this actual atom, one actual atom in the crystal. So when another atom is brought from the far away distance toward the actual atom in the crystal, so let's take it distance by distance. What will happen when the interatomic distance between these two atoms is at what distance? What will be happening in the energy levels? Let's try to see. If the interatomic spacing of silicon atom is very large, that means greater than this D, there is no interaction between what the actual atom in the crystal and the far away atom that is going to be brought. Because being far away, there will not be no interatomic interaction. Each atom in the crystals behave as a free atom. In this situation, each of the n atom has its own identical energy levels, which will give a sharp energy level or energy line, we can say. The electronic configuration, we know that from it. In the electronic configuration, we know that these up to this 1s2, 2s2, 2p6, these are ion core state, and these 3s2 and 3p2, these are valence electrons. Now see, this shows that the outer two subcells of silicon atom contain 2 electrons in 3s subcell and 2 electrons in the 3p subcell, whereas 6 electrons are required to completely fill these 3p subcells. Thus in silicon crystal under study, there are twice n electron filling twice n possible 3s level, all of which are of the same energy. There are 6n possible 3p levels, out of which only 2n levels are filled, and all the filled 3p levels have the same energy. Now next, let's see. When the interatomic spacing R is less than D but greater than C, that means in between these, there is no visible splitting of energy level if the distance or if the atom that is brought is somewhere here. So there is no splitting in these energy levels we see as a fine lines. For this inner ion core, electron energy levels will remain as a fine line like this, because this will not take any splitting or any change in its energy levels, because they are tightly bound by the atom, by the nucleus, and so there will not be no interaction. Only interaction or modification will take place in these valence electrons, the energy levels of the valence electrons, I mean. So when the interatomic spacing, this distance r is equal to c, at this c, let's see what happened. The outermost shell 3s2 and 3p2 of neighboring silicon atoms become appreciable at this point. As a result, the energy of the electron corresponding to 3s and 3p level atoms start changing. Changing what? Changing, the splitting of the energy level commences, whereas there is no change in the energy levels of the inner ion core shells. When the interatomic spacing r lies between b and c, in this between b and c, the energy of the electron corresponding to 3s and 3p levels of each atom gets slightly changed. Instead of a single 3s and 3p levels, we get a large number of closely packed levels, twice n levels corresponding to a single 3s or what 3p levels, when get a large number of closely packed levels. Got it? So what happened? 2n levels corresponding to a single 3s levels and 6n levels for a single 3p levels of an isolated atom. This spreading of energy corresponding to 3s and 3p level for a single what p level of an isolated atom, then what happened? This is a spreading of these energy levels, because we call it these as energy band, because here there are large number of atoms in the crystal. N is a very large, it will be of the order of 10 to the power 29 atoms per meter cube, and the energy levels between 3s energy level of 3s and 3p level is of a few electron volt. So the level due to this spreading of this energy of 3s and 3p level are very closely spaced, and this collection of closely spaced level we call it as what? Energy bands. Now next, let's try to see the splitting or the change in the energy level when the atom is brought in between what? This A and B. That means when the interatomic spacing r is greater than A but less than B. That means when you try to bring that another atom little bit somewhere here like this, let's see. The energy gap between 3s and 3p. Okay, this is 3s actually, this is 3p. Here what happened? There will not be no separation between 3s level and 3p level when you come closer and closer to what the actual lattice spacing A. What happened? There will not be any separation between this 3s level and 3p level. It seems that it is continuous. We can only say here that this is for 3s, this is for 3s. We can't say like that. It is not possible to distinguish between electrons belonging to 3s or 3p subcells, we can say. We can only say that 4n levels of 4n levels are filled and 4n levels are empty in this region. Now when the interatomic spacing r becomes equal to A, that means this is the actual lattice spacing in the crystal. At absolute zero, what happened? The 4n filled energy level is separated from the 4n unfilled energy levels, and the distance of separation in the energy level, we call it this separation between this 4n completely empty and 4n completely filled energy band. We call it that gap as band gap or energy gap, and it is denoted by what? EG. The lower completely filled band is called what? Balance band. This one we call it as balance band because this is the completely filled 4n energy levels, okay, of those electrons of 4n, and 4n energy levels, these are completely empty, and we call it this as conduction band. Now here we can see also here in this diagram that these are the 4n states of those 3s and 3p2. So in the 3s there are 2 electron, in the 3p there are 2 electron. When n number of atoms are contained in a crystal of semiconductor, naturally there will be 4n levels. Okay, 4n levels, because 4n electrons are there, so for them there will be 4n levels, and these 4n levels are very closely packed, and it will be as if just like a band of energy. We call it that band of energy as valence band, and this will be completely filled because 3s2 and 3p2, those 2 electrons are filled. But in that 3p2, out of that 6, only 2 are filled, so 4 are empty. So 4n levels, or 4n levels, 4n number of electron levels will be empty, and we call it these as empty levels. For an empty level as conduction band. Only when electrons jump by overcoming the energy from somewhere else, from the sun, from external sources, or it may be from the heat, or it may be from the applied source, if this energy gap can overcome by those electron in the valence band, it can jump to the conduction band, and then only conduction is achieved. Now let's see the difference between the conductor, semiconductor and insulator in terms of the band energy. In metal, what happened? Conduction band and the valence band are either overlap each other or partially filled. Conduction band is there. Hence, there is no energy gap in metals. Example of metal are copper or aluminum. In semiconductor, the energy gap is of the order of 0.7 electron volt for germanium and 1.1 electron volt for silicon. It has been generally taken that if the energy gap is less than 3 electron volt, then it will come under the category of semiconductor. But in the case of insulator, if it is coming of the order of 7, okay, in the case of insulator, if the energy gap is greater than that 3 electron volt, then it will be under the category of insulator. So insulator will have energy gap of around or greater than 3 electron volt. For example, in the case of diamond, energy gap is of 6 electron volt. So due to this large energy gap, no electron is able to go from the valence band to the conduction band, even if the applied electric field is very large also. Hence, electrical conduction in this material is impossible, as they behave as insulator. That means no conduction of electric current. Now let's see what is meant by Fermi energy and Fermi level. The maximum possible of energy possessed by free electron at absolute zero. This at absolute zero, this is very important. You should not miss it. This at absolute zero, this is very important. So what happened? The Fermi level, the Fermi energy means what? It is a maximum energy possessed by free electrons at absolute zero is called Fermi energy of that material. The energy level in the energy band diagram of semiconductor, as we are considering about semiconductor, let's concentrate it in the semiconductor. So the energy level in the energy band diagram of semiconductor, for which the probability of occupancy of free electron and holes become half, is called Fermi level. If the electrons get enough energy to go beyond this level and to reach to the conduction band, then only conduction take place. Otherwise, there will not be no conduction. Now, this is the energy band diagram for different materials. So either we can say this how this material can be classified into three: metals, semiconductor, insulator, in terms of energy band diagram or energy bands. In lower class we have classified these three material in terms of their conductivity, that in the case of conductor, the conductivity is of the order of 10 to the power 8 to 10 square, that means 100 Simon per meter. In the case of semiconductor, the conductivity lies between 10 to the power 5 to 1 Simon per meter. But in the case of insulator, the conductivity is less than 10 to the power minus 8 Simon per meter. That classification is in terms of the conductivity of the electric current through these different materials. But now in our case, the classification is in terms of the band diagram, energy bands, you can say. If this direction represents the electron energy, and this represents the conduction band. From here to here is conduction band, from here to here is valence band. So what happened in the case of this metal or conductor? What happened? Either we can say this valence band is overlapping with the conduction band. So from here to here is conduction band, from here to here is your valence band. So the Fermi level is there just above this conduction band. So what happened when electron is above this Fermi level and it reaches to the conduction band, then only conduction can take place. But in this case, what happened? Some electrons are already there above the Fermi level, because this portion somewhere here, it is also in the valence band as well as also in the conduction band, well above its Fermi level. Or we can also say in the case of metals or conductor, that this valence band is partially filled and this conduction band is also partially empty. So that means some electrons are already there in the conduction band, and what happened? There is no energy gap between valence band and conduction band. We can say like that. Got it? In the case of semiconductor, what happened? This is completely filled valence band, completely empty conduction band at 0 temperature or 0 Kelvin. But at a room temperature, what happens? Some electrons might have reached this conduction band well above this Fermi level, because from the external source like that of heat, or it may be from the external applied field, what happens? Some electron can jump that much energy gap of around, say, that 0.7 in the case of germanium and 1.1 in the case of silicon, can be achieved very easily from some external sources. And so this electron can jump above this Fermi level and can reach up to the conduction band, and then what happened? Conduction can be easily established. But in the case of this insulator, what happened? The energy gap or the band gap between the valence band and the conduction band. Valence band is completely filled, conduction band is completely empty. Okay, the energy gap between this highest of this valence band and the lowest of this conduction band, the distance between this energy gap, we call it that gap as energy gap or band gap, and this gap in the case of insulator is very large, around say 7 electron volt, okay, or greater than 3 electron volt, you can say. Got it? So this energy gap is very large, and so none of the valence electron in the valence band cannot jump up to that energy level above this Fermi level so as to reach this conduction band. So what conduction cannot be what established. Now let's try to see some of the what intrinsic semiconductor. Your semiconductor can be divided into two, intrinsic as and extrinsic. Intrinsic means pure semiconductor. Pure semiconductor means the semiconducting atom in the crystal itself. What happen, all the atoms present in the semiconductor material or semiconductor crystal will be all semiconductor atom. Either it may be pure silicon. In the case of silicon crystal, it will be pure silicon atom will be there in its, like this. In the case of germanium, it will be pure germanium atoms are there. No other impurity atoms are present, and those type of intrinsic, those type of semiconductor, we call it as intrinsic semiconductor. But such type of intrinsic semiconductor, the energy gap is around 0.72, and the conduction band is totally empty. Since no electron is available for conduction, therefore what the semiconductor atom at 0 Kelvin acts just like as an electrical, just like as an insulator, and so what happened, no electrical conductivity is possible in the case of those intrinsic semiconductor at 0 Kelvin. Okay, and what happened, this the conduction is possible if some of the electron breaks the covalent bond from this atom and it becomes free, then only what happened, conduction is achieved. As the this breaking of covalent bond, it will require a minimum energy of around 0.72 electron volt in the case of germanium, and 1.1 electron volt for that of silicon. It is equivalent to that of energy gap. Okay, let's see. Now whatever I have told you here it will be all coming here again. Now in the intrinsic semiconductor, the number of thermally generated electron always equal to the number of holes. Now if you go back to the previous slide, then you will see that this number of electrons, okay, these are having covalent bonds. One silicon atom here in its outermost shell, that means valence shell, 4 electrons are there. Let's take it that these and these are what for this atom. So another remaining 4 atom, they will have what covalent bonds from the neighboring atom. Suppose if you take it these, then this electron, this, let's take it the second one, okay, this as the valence electron for this atom. So the first electron, this one and this one is not for this atom, rather they are sharing or having a covalent bond with this atom. This atom has this electron is from this atom, this electron is also from this atom, this electron is also from this atom. So they will have a covalent bond. Until and unless this covalent bond is break up, then there will not be no free electron. If there is no free electron, then there will not be no possibility of conduction. So at 0 Kelvin, what happens, there is no free electron available, and so no conductivity is possible. But by having, this is in the case of 0 Kelvin, but if you little bit increase its temperature, due from that thermal energy, the covalent bond may be break up and free electrons will be available. Suppose if the covalent bond is break up from here, then what happen, electron will come out from that atom and it will be free to move about. If that electron comes out, then what happens? It will leave a space known as hole. Hole is nothing but this is the empty space of electron, and it just act just like a positive. Its behavior is just like a positive charge, and we can call it that hole as simply hole, which will be equivalent to the positive charge in the case of electron. So when electron covalent bond is break up, one electron will be released, and then what happen? It will become hole there. So what happened? The number of thermally generated electron and the number of hole in the case of intrinsic semiconductor will be what? Same. The number will be same. That is what in the first number 1 point. In intrinsic semiconductor, the number of thermally generated electrons always equal to the number of holes. So if Ni and Pi are the concentration of electrons and holes respectively, then Ni equal to Pi. This quantity Ni and Pi is referred to intrinsic carrier concentration. Now let's go to doping, just to come to that of the impurity semiconductor, or rather we can call it as extrinsic semiconductor. So we need this process known as doping. What is this doping? Doping is the process of deliberate addition of a very small amount of impurity atom in an intrinsic semiconductor. In an intrinsic semiconductor, if you deliberately add a control amount of this impurity atom into this intrinsic semiconductor, then that process of deliberate addition of this impurity atom to that intrinsic semiconductor, we call it as doping. The impurity atom so added, we call it that as dopant. The semiconductor containing impurity atom is known as impure or extrinsic semiconductor. So there are three processes of doping. Doping can be done in either of these three ways. What are those three ways? Let's see. By adding the impurity atom in the molten state of semiconductor, okay? That is the first one. That means in the molten semiconductor, we need to add what? Impurity atom. Next, we can also achieve we can produce this extrinsic semiconductor by hitting the crystalline semiconductor in the atmosphere containing the dopant atom. And in it, what happens? The dopant atom will exactly replace the semiconducting atoms from the semiconductor crystal, okay? Yes, the last one is what? By bombarding the semiconductor with the dopant atom. That is the last one, bombarding the semiconductor with the dopant atoms, right? Let's see the extrinsic semiconductor. In the n-type extrinsic semiconductor, we can divide it into n-type semiconductors and p-type semiconductors. In short, we can say extrinsic semiconductor can be classified into two. The first one is n-type semiconductor and the second one is p-type semiconductor. Let's try to know in depth about n-type semiconductor and p-type semiconductor. N-type semiconductor is formed by doping pentavalent atom, okay, to the intrinsic semiconductor. Pentavalent means having 5 valence electrons. Got it? Or valency 5. So like that of what? This pentavalent atom, it may be like that of what? Your phosphorus, okay, or your arsenic, your antimony, bismuth, like that of such pentavalent atoms can be added to this impurity atom, to these pure semiconducting atoms. If it is replaced, then that resulting material we will call it as n-type semiconductor. Now let's try to replace these semiconductor atom by a pentavalent atom. Let's take it as phosphorus, red for phosphorus here. So what happened in the phosphorus atom? It has 5 valency. So there are 5 electrons in its valence shell because this is a pentavalent atom. So what happened? Or in the pentavalent atom, out of the 5 electron valence electron, I mean 4 will be what use up in having or in forming covalent bonds with these neighboring 4 silicon atoms. But there is one electron in excess and it has no counterpart of another electron of this another atom to form covalent bond. So this electron will have what, an extra electron. So one lone electron will be always there for every pentavalent atom added. The number of pentavalent atom added will be equal to this number of electron, excess electron there in the extrinsic semiconductor. So what happened? And this lone electron, which has no counterpart to have covalent bond, it has more energy comparative to those other electrons, and it can move about freely in the crystal. Thus, each impurity atom added donates one free electron to the crystal structure. These impurity atom which donate free electron for conduction are called donor atom. We call it this as donor atom. So on giving off their 5th electron, the donor atom become positive charge. If it is giving out, then this will carry what, positive charge. However, the material remains electrically neutral as a whole. At a room temperature, some of the covalent bonds may get ruptured from somewhere here. Covalent bond may get ruptured, producing thereby free electrons and equal number of holes in the n-type semiconductor. But overall, the total number of holes in the n-type semiconductor is relatively small than that of the electrons. Hence, in an n-type semiconductor, electrons which are more in number, so electrons we say they are majority charge carrier, whereas less in number holes we will call it as minority charge carrier. So for that of the extrinsic semiconductor, energy band diagram can be represented like this. This is an n-type semiconductor, valence band here in the lower level, upper level we call it that as conduction band. This is completely empty and this completely filled, this is completely filled, and the conduction band is completely empty at 0 Kelvin. But when this impurity pentavalent atom is added, there is a lone electron there. So for this electron, the energy level is well above this valence band, but it goes up and it comes below the conduction band, just below the conduction band. This is the donor electrons. These electrons which are free to move have higher energy than those of the electron in the valence band. So this electron will have less energy than that of the free electron. When it moves out, it will be free and it carry what higher energy, and this electron which moves freely we call it those as donor electron, and these donor electrons, its energy level is much higher than those of the electrons, and it comes near to that of the conduction band but below the conduction band, and this will makes it that conduction more easier, slightly energy getting from some external agent, then what happened, conduction can be achieved in the case of n-type semiconductor. Now let's go to that of the p-type semiconductor. This is for the doping done with the impurity atom pentavalent arsenic. Okay, same as that was before. So one lone electron is there after having those 4 electron forming covalent bond with the neighboring force germanium. Okay, yes, let's see for the p-type semiconductor. P-type means what? It is the doping will be done with a trivalent atom in the case of this p-type semiconductor. So what happens if p-type is formed by doping what? Trivalent impurity atom to the pure intrinsic semiconductor. Suppose your trivalent atom here is boron, so you can also take your trivalent atom like gallium, indium, boron, here aluminum, like that. Okay, you can take it all those trivalent atoms just to replace one semiconductor atom from it. Now this trivalent atom, we know that tri means 3, so this boron trivalent atom will have only 3 electrons, okay, 1 2 3 like that, and so it will form what covalent bonds with a 3 neighboring pure silicon atom. But for this neighboring silicon atom, there is no counterpart or what electron from this trivalent boron atom, so it will leave a space there for an electron, so we call it that empty space of an electron as whole. So for each and every trivalent atom added onto this intrinsic semiconductor, there will be a hole created. So the number of trivalent atom added will be equal to the number of holes what created. Got it? So this empty space of electron, it is equivalent to the positive charge, so we call it this as what, p for positive, so we call it p type. In the case of n type, number of electron is more, electron means n, so we call it that n type. Here what happened, the number of hole will be more than the number of electron generated, okay, by after increasing the temperature, the covalent bond may be break up. In that case, what happened, number of electron and number of hole will be same. But if pentavalent trivalent atoms are added, then the number of holes will be more than the number of electron. So number of hole in this case of p type will be more than the number of electrons. So holes are the majority charge carriers and electrons are the minority charge carrier in the case of p type, opposite to that of the n type semiconductor, okay. Now what happened in the energy band diagram, when we look to that energy band diagram, this is completely filled what valence band and completely empty conduction band in the case of 0 Kelvin, in the case of what p type semiconductor at 0 Kelvin, I mean. So what happened, these what acceptor hole, why we call it acceptor, it can accept one electron from somewhere else. By after breaking the covalent bond, one electron can come and reside here, so that means this atom can accept electron, so we call it this atom as what, acceptor atom. After accepting one electron, okay, from somewhere else, this acceptor atom will get what, negative charge, otherwise as a whole it is neutral, okay. So even though the number of holes are more than the number of electron in the case of p type semiconductor, what happened, as a whole p type semiconductor is electrically neutral. Now those acceptor acceptor hole, the energy level for this acceptor hole is above that of the valence band, but in the case of n type, that what, donor electron energy level was somewhere here below the conduction band. But in the case of what, p type, acceptor hole energy levels are above the valence band. Got it? When electrons from the valence in the valence band, if they get some more energy which is equal to the energy gap, then only they can jump to the conduction band and they can reach this conduction band and conduction is achieved. Now this is a broad difference between the p type and n type that we have just discussed. So your acceptor hole's energy level is just above the valence band, whereas your donor electron energy level is just below the conduction band. So conduction will be much easier in the case of n-type semiconductors when we compare to that of the p-type semiconductors. And when we compare with your pure semiconductor intrinsic and that of the impure extrinsic semiconductor, in that case what happened, your external extrinsic semiconductor will be having more conductivity than of pure intrinsic semiconductor. Now let's see the distinction between intrinsic and extrinsic semiconductors. Now these intrinsic semiconductors are pure group 4 element, that means tetravalent. Extrinsic semiconductor, these are what, either group 3 or group 4 added to that of the group 4, got it, element. That means to that of pure group 4 element, if we add what, either trivalent or pentavalent, then it comes extrinsic semiconductor. Conductivity, if you compare with the conductivity is very less in the case of intrinsic semiconductor, but it is greatly increased in the case of extrinsic semiconductor. The number of holes, that means the number of thermally generated holes and free electrons, are same in the case of intrinsic semiconductor, but these are very small in number because these holes and electrons are thermally generated after increasing some temperature to some level of temperature. Then they break the covalent bond and form these free electrons and holes. So their numbers are always equal, but the number should be very small. But in the case of extrinsic semiconductor, number of electron and number of holes are not same. Conductivity increases with rise in temperature in the case of semiconductor, because as temperature increases, what more and more covalent bond may be break up, and so more and more number of electron and holes are increased. So what happen, these electron and holes, which are the current carriers, naturally conductivity will increase with a rise in temperature. And here also in this extrinsic semiconductor, conductivity depends upon, no doubt, with the temperature, and moreover it depends on the amount of the impurity added. Okay, impurity atom added. More number of impurity atom added, more conductivity. But one thing to be noted, that we cannot replace all the semiconductor atoms by that impurity atom. If it is done like that, it will not have that conductivity of that much like this extrinsic semiconductor. Got it? There will not be no more semiconductor rather. Now last point, the number of hole is always equal to the number of free electrons that we have seen. But in the case of extrinsic semiconductor, in the n type, what happened, number of electrons is very much greater than number of holes. So in the case of n type semiconductor, electrons are the majority charge carrier, holes are the minority charge carrier. In the p type, what happened, number of electron is less than number of holes. So holes are the majority charge carrier. Holes are the majority charge carrier and electrons are the minority charge carrier. So let's try to see the summary, a brief summary of all those what we have discussed. Now it is better to do like this. Let me do like this. Okay, let me take to the first one. So we know that your what initially at the time of this, when we are trying to find some semiconducting device, we were using what electronic valves or what electronic valves we use, and these valves are very large in size, very bulky, and operates at a high voltage, and it consumes large amount of power. And what happened, they are not reliable, and their operating voltage is also very high, of the more than that of the 100 volt. And if you are going to use now, we cannot just switch on now and we can't use it. It needs some operating time also. Beforehand we need to switch on first, and then after some time it can operate it. That was like that. But in the case of semiconductor devices, what happened, these are very small in size, what operates at low voltage, consume less power, and these are what very much reliable, and at the same time their lifespan is also very long. So we use it such type of semiconductors, and such type of semiconductors like diode, transistors, this leads to the development of what we known as ICs, integrated circuits, whereby large network of circuits consisting of such components can be packed into a small space or small chip, and we call it that as what integrated circuits, which are nothing but the hearts of all modern electronic gadgets. Got it? Yes, according to the quantum mechanical laws like that of Bohr's theory, we know that a free atom, okay, cannot have what arbitrary values, but only some definite quantized values should be there. It means that the electrons of those what isolated atom will have a definite energy levels. But when we come to that of the crystal structures, what happen, the inner core cells, the levels of those electrons of the energy core cells will not appreciably change in the energy levels, but those energy levels of the valence electrons is considerably what appreciably modified, and it is due to the fact that these valence electrons, the levels of these valence I mean the electrons of the valence cells are what interacting or sharing with that of the neighboring what atoms. Because of that, what happened, there will be appreciable change in the energy levels of those valence electrons. Now these are the formation of those what energy bands. Let's see. So what happened when the electron, the energy levels of the inner core cells will not be changed, rather the energy levels of the valence cells considerably changes when that atoms are brought close and close toward the actual lattice spacing. Suppose when one atom is here, another atom is here, at this distance somewhere there, one atom may be somewhere here, another atom may be somewhere here, another atom may be somewhere there at the back, like that. So when all these atoms are brought close to this actual what position of the atom, then what happen, the energy levels of these valence what electrons or subcells, this can be modified, and we come to know that this lower energy level, okay, these are closely spaced energy levels of those what 4n levels. Got it? If capital N is the number of atoms of the crystal of the silicon, then there will be 4n levels which are very closely packed, and we call it those level as valence band. And these are for 4n levels. Actually it is of that of 4p 3p I mean, so p levels. So all those 4n levels are here, and these are also very closely packed, and so we call it that as conduction band. In the actual semiconductor at 0 Kelvin, these valence band are completely filled, and these 4n levels, what we call as conduction band, these are completely empty, but these are allowed energy levels. Electrons are not there, but when electrons can come to that energy level, then electron can come to this state, and electron will take part in the conductivity of the semiconductor. So the energy gap between these highest what valence band, we call it that as EV, and that of the lowest energy level of the conduction band, we call it that as EC. So the energy gap between EV and EC, we call it that as forbidden energy gap. Got it? Yes, this is about that what I have just said. Now in the case of metal, what happened, metal can be either energy band, I mean it can be either overlapping between conduction band and valence band, or we can say partially filled conduction band. Okay, there is no energy gap in the case of metal, so what happened, conduction is achieved very easily without having any external energy. If a small field is applied, then conduction will take place. In the case of semiconductor, what happened, energy gap is less than that of 3 electron volt, and so in the case of germanium it is 0.7 electron volt and 1.1 electron volt in the case of silicon. So the energy gap is very small. But in the case of insulator, the energy gap is much greater than that of 3 electron volt. It is coming out of the order of 7 electron volt if it is set like that, of the order actually, okay, it may be around 7 electron volt, that is a meaning. So what happened in the case of diamond, it is 6 electron volt. I have given you the example, right? So this is about the Fermi energy, the maximum possible energy possessed by the free electron of the semiconductor at that 0 Kelvin. We call it as Fermi energy, and that of the occupancy of the free electron and hole. Why? Because we are taking free electron and hole, because this movement or motion of free electron and holes in combine contribute the electric current, the current in that semiconductor. So halfway in between what that of the free electron and holes, the energy level, we call it as what? Fermi level. If the electron gets enough energy to go beyond this level, then conduction takes place. That I have told you. Okay, this is about that of the what energy band diagram. In the case of metal, they overlap, valence band and conduction band. In the case of semiconductor, the energy gap is very small, and the Fermi level is halfway between this conduction band and the valence band. Okay, halfway in between this gap, I mean. But in the case of insulator, the energy gap is very high, rather than what 3 electron volt, and it may be coming around 6-7 electron volt. And so what happened, as this energy gap is very large, none of the electron in the valence band can have that much energy required to reach to the conduction band, so it can't conduct electric current. This is about a pure silicon. We have an intrinsic semiconductor. We know that what happened, the number of thermally generated electrons and the number of thermally generated holes are equal. Ni is equal to Pi. Doping is a deliberate addition of a very small amount of impurity atoms into an intrinsic semiconductor. Mind you that in this process of doping, it should be deliberate addition of the impurity atoms in a very controlled manner, and the impurity atom so added, we call it as dopant. The semiconductor containing impurity atom, we call it as extrinsic semiconductor. And in the doping, we can do doping in 3 ways: by adding impurity atom to the molten state of the semiconductors, by heating the semiconductor in the atmosphere of a dopant atom so that it diffuses into the semiconductor, and lastly by bombarding the semiconductor with the dopant atoms. This is about the intrinsic extrinsic what n-type semiconductor. Here we have to replace the semiconductor atom by a pentavalent atom. Here in our case I use phosphorus. So whenever phosphorus is added, after having that out of that 5 electron in the pentavalent atom, 5 valence electron, I mean 4 have been used up in forming covalent bonds with the neighboring semiconductors atom, and 1 electron is there, okay, for every pentavalent atom. So this extra electron is created for every pentavalent atom, and now we call it this pentavalent atom as what? Donor atom, because it can donate 1 electron from each valence shell. So what happens when this electron is donated somewhere or jump to somewhere else, then what happen, it will carry what? Positive charge. Now your donor electron, the energy level of a donor electron is just below the conduction band and close to the conduction band, not in between what valence band and conduction band, rather it is very close to the conduction band, just below the conduction band. But in the case of p-type, and this is about the n-type semiconductor, when instead of phosphorus, here it has been replaced by arsenic. And it is also same in the case of germanium. What happened, out of the 5 electrons, what happened, 4 will be forming covalent bond with this neighboring 4 germanium atom, and 1 lone electron is there, and this will donate electron when it jumps to somewhere else. Same is the case in the previous slide. Now in the case of this p-type semiconductor, what happened, we have to dope it with a trivalent atom. Your semiconductor atom will be replaced by a trivalent atom like that of boron, indium, aluminium, like that. Now what happened, it has only trivalent, means only 3 electron in the outermost shell, so 3 will form covalent bonds, and there is 1 lack of electron to have covalent bond with this neighboring atom. So this empty space of electron, we call it as hole. So for every trivalent atom added, 1 hole will be created, and the donor, we call it this as what? Acceptor, not donor, because it can accept 1 electron from somewhere else, and so it can accept electron, means what we call it this as acceptor atom, and when it accept one electron it will carry negative charge. The acceptor hole level is just above the valence band, so whenever the valence electron from somewhere from this valence band jump up to the conduction band, then only it can conduct it. Okay, so let's see, this is a difference, a brief, just to what compare the energy band diagram for n type and p type. In the case of p type, what happens, acceptor hole is just above the valence band, and in the case of n type, your donor electron level is just below the conduction band. Let's see the different properties of what intrinsic and extrinsic semiconductor in a brief way. Intrinsic means what, group 4 element. Extrinsic means it can be either doped with group 3 or trivalent or pentavalent into the intrinsic semiconductor. Conductivity is low in the case of intrinsic, whereas conductivity is greatly enhanced in the extrinsic semiconductor. The number of free electrons and holes in the case of what intrinsic semiconductor are equal, and it should be small. Number of electron and number of holes in the extrinsic semiconductors are not same. Conductivity increases with the rise in temperature. Why? Because when with the increase in temperature, more and more covalent bond may be broken up. So what happen, number of electron holes created will be more. Conductivity depends on the other side of the extrinsic semiconductor. Conductivity depends not only on the temperature, rather it depends upon the amount of the impurity atom added. In the case of intrinsic semiconductor number 5, the number of hole is always equal to the number of free electrons that we have said here. But in the case of extrinsic semiconductor in n type, number of electron is very much greater than the number of holes, whereas in the case of p type, what happened, number of holes is greater than number of electrons. Now I will give you some homework, or rather home assignment. The first one is choose the correct answer. Question number 1. At 0 Kelvin, the conduction band in solid is partially filled. The solid sample is conductor, B semiconductor, C insulator, D none of this. You have to choose it, which one is correct. Question number 2. In the n-type semiconductor, number of electron is very much greater than number of holes. What is the nature of the charge possessed by the semiconductor? You have to say what is the nature of that n-type semiconductor. Okay, whether it is negative, positive, or neutral, and you have to give the reason to support your answer. Okay, that's all. That will be the end of our today's class. Okay, thank you.